Distributed systems are really the backbone of everything that a normal developer would work with, be it databases, their replicas, microservices, and there are some anti-patterns that you should be aware of. First one being a single point of failure. You should always make sure that you don't have a single point of failure. What do I mean? Let's imagine this use case where a user tries to fetch some data and the request goes through a service that then contacts this database. What happens if this database is gone? Let's say the container died, right? We don't have any data anymore. What you should do instead is always make sure that your database doesn't only have a backup, because backups are for disaster recovery, but you should always have replicas, meaning every time the primary database gets updated, this update should also be reflected either synchronously or asynchronously in a database replica. And in distributed systems, you would usually have multiple replicas depending on the database and its method that it uses. So keep this in mind. And the same applies for normal services that are serving the requests, meaning try not to have only one service, but try to have two services at least, and do load balancing. Load balancing obviously will be done with a separate component that's called a load balancer, which is going to distribute the requests to either of the services based on how busy they are at the moment, for example. All right. The second point is chattiness or over communication. Sometimes services are communicating way too much with each other and they're exchanging the requests back and forth, and this is really costing you the bandwidth. So in order to get rid of this extra bandwidth that you normally don't need, you should be aware of the fact that you might need to optimize some parts of your application. For example, let's say you optimize this part, so service A is really modular and not dependent on service B that much, but now you're making requests to the database, and these are your requests. So you try to fetch users, at least 100 users with a limit 100, and then you try to fetch the orders for each user that you fetched above, okay? So this is going to be 101 requests in total. This is a lot. This is chattiness, and you don't want to be bombarding your database with so many requests just to fetch this kind of data. What instead you should do is use something like a left join, all right? Use the join because you will be able to fetch the data from the first database users and fetch the data from orders at the same time. All right, so keep this in mind and make sure that your services and your databases don't exchange the data all the time with each other, that they are optimized and batched whenever it needs to be. All right, the third point that I want to bring up is ambiguous ownership. This is something that I really see in systems that are not really architected well. So let's say we have two services and they're all contacting the same database. Totally fine, right? You can have this kind of an architecture in microservices where two microservices are contacting the same database. But the issue starts when the service A is trying to fetch the data from the same table or modify it, and service B is also trying to not usually fetch, but usually the issue is in modifying this table. If two different services are modifying the same table, you have to start analyzing this, whether this is a bottleneck or not. Because this tells me that service A and service B don't have clearly defined boundaries and ownerships. Who's owning this service or this table? This table should be primarily owned by a single service. This table here on the very right should be primarily owned by another service, let's say service B, meaning at least I would say 80 to 90% of the requests should be coming from one single service. And if you see that this table is used 50% of the time by service A and 50% of the time by service B, then I clearly can tell that you have an issue with ownership there. Your boundaries are not clearly defined, so you need to work on that. All right. My next point would be eventual consistency and the fact that a lot of developers and teams really do misunderstand that. So one of the things that's good for distributed systems is asynchronity. All right. And we get this asynchronity when we used some message buses, right? Message bus or queues. Let's say it's a Kafka or RabbitMQ, right? And this makes our system asynchronous. It makes our system event-driven. I actually have loads of videos on event-driven development, and I use Kafka extensively. But a lot of it really changes your system. So now your system is not synchronous anymore, it's asynchronous. When it's asynchronous, it means it's eventually consistent. So you don't have strong consistency anymore. Let me give you an example. Let's say the user tries to upload a new image on their profile, and this service is saving this image. And it's first saved in the first database. Let's say it ended up in its primary. And at the same time, your friend is making a request, and the service trying to fetch this photo or your profile photo from the second database. But this image has not been synchronized to the replica yet. It's in the primary database, but not in a replica. So your friend is still going to get your old photo, right? So this is called eventual consistency. Eventual consistency basically means that if no further writes happen, replicas eventually agree, meaning this photo is going to be eventually here. So this is kind of a different paradigm compared to what you would have in a synchronous case. In a strong consistency, you would have exactly two databases, and they would have to be synced as well. So this photo would eventually come here, but your first database would not say that, hey, I have saved this image, unless all the primaries have also acknowledged that they have saved this picture as well. This is the main difference. And if you opt in for event-driven architecture, you should be aware of that your system is mostly eventually consistent. All right. Now, the fifth point is overuse of synchronous communication. Sometimes it's okay not to have an event-driven development or event-driven architecture, but have an synchronous architecture. So your services are communicating synchronously. And let's say if you notice that you have one service that's contacting another service, and then another service is contacting the third service, and your first service has to wait for all that trip that goes chain by chain to another service, maybe this is the sign that you should opt in for an event-driven architecture. All right. So as soon as you notice that you have like a long chain of requests and one of the services is idling, introducing event-driven architecture is actually the right way, because service A can return the answer to the user right away. And all of this processing, let's say processing within the service B and service C, can pretty much happen in the background over the message bus, over, let's say, a Saga design pattern. Actually, I'm making a video on the Saga design pattern next week, so check it out, and don't forget to subscribe so that it pops up on your feed. Now, the last point I want to make is circuit breakers. All right, circuit breakers are important because let's say you have two services, or even let's say, sure, you do have a synchronous architecture and you do have three services. What's going to happen is the following. When the service A makes a request to service B and service B makes a request to service C, this should be C here, and let's say service C fails. Okay, service C fails, and this problem is pretty much going to cascade back. Service B is going to realize, oh, I cannot contact service C anymore, and service B is going to go down. So it's pretty much broken. It cannot serve anything because it does rely on service C. And since service A relies on service B, A is also going to be non-functioning. So circuit breakers, or this whole pattern, is telling you that you should take this into account. This kind of an issue can result in a retry storm. So the service B is going to keep retrying, and even if service C can in fact restart or recover from the error, it's going to be bombarded by the requests from service B and never going to be able to functionally or function under this load. Same is happening with service B. It's down, it's trying to restart, but since we're bombarding it from the service A, it's gonna have a lot of load and probably gonna crash as soon as it starts. So you should introduce circuit breakers. I also have a video on circuit breakers, so go check it out to have a deep dive. You can introduce exponential backoff, meaning service B doesn't bombard service C, but it retries, let's say, 1 second, and then if that didn't work, it retries every 5 seconds. If 2 times failed, maybe retry in the next 30 seconds, and do it randomly so that there's no retry storm happening. Alright guys, I hope you learned something new. This was a quick video. If you did, smash like as always. I'm gonna see you in the next one. Goodbye.